Okay, so today we're going to look at the reaction mechanisms and rates part 2. And so we're going to start with this equation, 2a plus bc creating a2bc. And so we're just going to work with generic equations. You can apply the concepts to actual equations. Just once you get to the idea of how to work with just anything that's generic, because it's going to transfer over to a real equation fairly easily. And so what I want you to do, what we're going to do first is we're going to propose a two-step mechanism to, uh, to for this reaction. Now, if you did a one-step mechanism, the one-step mechanism is the reaction, and so this actual reaction here, that would be the mechanism for a one-step mechanism because it all happens in one step. Now, again, the odds of this happening in this case are pretty low because you'd have to have 3 particles, 2 of the A particles, 1 of the BC particles colliding with sufficient energy in the proper orientation, and the odds of that happening are not very good. And so more than likely in this case, when we have 3 reactant particles, we are going to have a multi-step reaction mechanism. And so let's do a two-step mechanism. Let's propose a two-step mechanism. Now, the thing about reaction mechanisms, when you do multiple step mechanisms, is you really need to kind of just use your imagination a little bit so that you can come up with some kind of a mechanism that works. So it can be anything. If all you're asked to do is propose a mechanism, then just use your imagination to propose a mechanism. If we get into more data-driven stuff, then we'll have to check our mechanisms versus the data. So we're just proposing a mechanism here. So a possible first step in our mechanism could be that the 2A particles collide to create an intermediate particle, A2. And that would be the first step in the mechanism. The second step would be that intermediate particle, A2, collides with the BC particle in the chamber, and when those two particles collide, then we get the A2 BC particle, and that would be a second step mechanism. Now, you can use some logic here and think, hey, is this mechanism likely to occur or not? And just looking at this, I would say, hey, this is probably not the mechanism. The reason being this is because an intermediate in this mechanism is A2. Well, why wouldn't the two A's normally combine into A2 in nature if the intermediate's A2? Does that make sense? So we don't have A2 here. A2 is not likely to be a particle, A sub 2, because our reactants are not A2s, they're individual A atoms. And so I think this is probably an unlikely scenario to occur. So let's propose a different mechanism. Maybe a second possibility. So a second possibility for this reaction might be that one of the A molecules or particles combines with the BC particle, and that produces the intermediate ABC, and then that intermediate ABC combines with the other A particle that we didn't use in the first step, and that produces our A2BC product. And so I would, just looking at these two possible mechanisms, I would say, hey, this is unlikely, this is more likely. Not say this is the mechanism, this is more likely. Mechanisms can get very complex, and we're really just looking at the surface level of mechanisms. And so I would say that this is more likely to occur, this particular mechanism. So one thing about mechanisms, when you do create them, or invent them, if you will, out of thin air, is that the mechanism needs to add up to the reaction, and that seems fairly obvious. But it has to equal the reaction. Otherwise, your mechanism's it's not even theoretically possible. And so, as an example, in these first two-step mechanisms here on this first one that we did, on the left side and the reactant side, we have 2A particles right there. So 2A particles. We have a BC particle, and we produce an A2BC particle. and the intermediate A2 is on both sides, and so they cancel. And so the two mechanism steps sum to the overall reaction. And you can check this other mechanism as well to make sure that it's right. So when you're doing these mechanisms, so we have A and A, so there's our two A's and our BC. So 2A's plus BC, and there's our A2BC, and the intermediate ABC cancels out. If your mechanisms don't do that, then you have an invalid attempt at a mechanism. They have to sum to the overall reaction. Okay? So let's do another example. All right, so here's our second one. 2AB2 creates or decomposes to form 2AB plus B2. And so let's propose a possible mechanism for this decomposition reaction. And so we could have step one in our mechanism may be that the AB2 molecule turns into AB plus B. Okay, so there's a possibility of what we have. All right, now step two. Now AB is one of the products, so that's good. We want to produce one of the products. That's actually a good tip. If possible, produce one of the products in your intermediate step. So we produced a product. Now this B component, that is not a product, so that's going to be an intermediary. So we need to take that intermediary and we need to use that in step two of our mechanism. So we use one of our AB2s over here. We have one left. We have an intermediate B, so we're going to combine those two things. So B plus AB2. Now this, we can get an AB out of that, which we need another AB out of it. So AB, and that would leave one of the B's out of the AB2s, and the B by itself, that's going to give us our B2. Okay, so if you sum this up, just like we did earlier, we're going to have an AB2, an AB2, so that's our 2AB, or 2AB2, sorry. Okay, we're going to have an AB and an AB, so that's our 2AB, and we have a B2, and the intermediate B is canceled out. Okay, so I've given you three examples, and we can do another. There can be another theoretical mechanism for this reaction, and so there can be other possibilities here. But I'm just trying to give you some ideas on, hey, just use your imagination, create these mechanisms. Now, when you create a mechanism, what you really want to do is you want to back it up with data, and so then you do labs and you try and find out the rate laws. Or the rate expression. So let's look at that component of this. All right, so let's go back to the first equation we looked at, and one of the particular mechanisms that we looked at. So this is the 2A plus BC making A2BC. And so here's our two-step mechanism. Now, there's lots of ways to ask questions about this. So let's look at it. If the first step, let's say that the first step is the slow step in the chemical reaction, that means it's the rate determining step. That means that the rate law or the rate extraction is going to be based upon that equation. And so if we looked at this and we said that the first step was the slow step, then the rate would be equal to K times the concentration of A, because it's one of the reactants in that step, times the concentration of BC, because it's one of the reactants in that step. And that's it. If you have a mechanism and you know the rate determining step, you have to know which step is rate determining. If you have a mechanism and you know the rate determining step, then you know the rate law. It's simply the reactants in the rate determining step. And so that is the rate law if step one is the rate determining step. Let's say that step two was, so we'll do that one in red to differentiate it. Let's say that step two was the slow step, and so it was the rate determining step. If we did the rate law there, it's going to be slightly different because we have to catch something here. Rate's equal to K, the ABC, concentration of ABC times the concentration of A. That might be what you'd put down if we followed this little rule here. But that would be wrong. And the reason why it is wrong is because ABC, this ABC particle, is not a reactant. Look up here in the original equation. We got A and we have BC. There is no ABC. And remember, rate laws must be based upon reactants. And so this is not correct. And so how are we going to handle the fact that we have an ABC in our quote-unquote rate expression? Well, we're going to backtrack this ABC to where did ABC come from? And so this ABC particle came from here, which came from over here. So there's an A component and a BC component to the ABC. So we're going to replace ABC with the reactant A and the reactant BC, and then we have our original A here as well. And so that gives us a new rate expression, K, A to the second, BC. And so A is a second order reactant in this reaction if step 2 is the rate determining step. Okay, and so that's how you handle determining the rate expression if you're given a reaction mechanism and you're told which reaction step is the slow step, then you don't have to do any math to find the rate the rate law of the reaction. So let's look at the second one that we did as well. All right, so looking at our second equation, and we propose this mechanism, here's a question that you might see. A student proposes the above mechanisms with step 1 being the rate determining step. Experiments show the rate expression to be rate equals K, AB2 raised to the second power. Is the student correct? And so pause the video for a second, look at it, and then restart and come back to me. So hopefully you took a chance to look here. If you didn't pause, shame on you. If you're looking at the rate that the student proposed, or the step 1 being the proposed rate determining step, and you compare that to the rate, well, if you look at step 1 being the rate determining step, you should say that the rate should be equal to K AB 2 without a power here. This would be to the first power here versus second. So comparing that to the experimental rate, that does not support the student's proposed mechanism and rate determining step. And so you would say the student is not correct. Okay? And it can go a lot further. And so is this mechanism even valid at all? Could this mechanism be a valid mechanism if that's the experimental rate? It could be if step 2 is the rate determining step. Because if you look at step 2 as rate determining step, you would have BAB to the second, but B is an intermediate which comes from AB2, so that's going to be 2 AB2s. And that would be a valid mechanism and rate determining step proposal for that chemical reaction. Okay, that's going to be it for today.